Hey everybody, in this video we are kicking off section 4, which is one of my favorite sections. One of my favorite things to do in math is solving exponential and logarithmic equations and using the one-to-one property, using the product quotient and power properties. I just find this section to be really enjoyable and nifty and really nice how it works. I really love the one-to-one property, so let's get into it. First thing we are going to do, what is the one-to-one property? So to know what the one-to-one property is, we need to remember a bit about the graphs of exponential and log, so we understand like when and where we are allowed to use it. So pulling this from our little vault of the examples we did just recently. So this is example 6 in perhaps section 2, maybe section 2 it was. I already forget. But here in blue you have an exponential graph, very basic, 2 to the x, and then we have log base 2 of x. These are inverses of each other. We say functions are one-to-one if they pass both the vertical line test, so here's the vertical line test on this blue exponential and it passes, you only ever cut it once, and the horizontal line test, thus meaning that the inverse will pass the vertical line test, thus telling us that the function and its inverse are both functions, thus telling us that these x and y relationships are one-to-one. No x goes to more than one y and no y goes to more than one x. They are in exclusive relationships and nobody is cheating on anybody else. What that allows us to do is to be very matter of fact with our work. And if you want to say, well, 2 to this power equals 2 to that power, therefore this must equal that, bing, bang, boom, you're eliminating tons of obstacles and making solving so much better. So let's see what that looks like in examples. All right. So here, this style of example is mental math friendly. I believe maybe it's example 2 or 3. We'll get into examples that are going to be less mental math friendly, if you will. They will require the use of a calculator. All right. So 2 to the, this is solved, 2 to the 3x minus 8 equals 16. So what we want to do is we want to set this up and make it so that we want a swap-opportunity, okay? And what you're thinking, what the heck is she talking about? What the heck is this swap-opportunity? So a swap-opportunity is an opportunity where you can swap out some big, beefy, high-calorie thing over here for a low-calorie thing, meaning find a smaller number raised to a power so that both sides can be, b to a power, b to a power. Make the bases match on both sides. So can we make 16 into 2 to a power, or could we rewrite the 16 and the 2 to both be the same number to a power? And since 2 is prime and it's not much I can do with it, it's pretty much locked in as 2 to the 3x minus 8. We can't change that. 16, many people might be like, oh, that's only 4 squared. What am I going to do about that? Well, that's okay. 16, while that's still 4 squared, it's also 2 to the 4th. Coincidentally, 4 squared, 2 to the 4th, flip-flopping. It's just coincidence, right? Now, this is where the one-to-one property comes in. 2 to the 3x minus 8 equals 2 to the 4. We could ignore the 2's. You are not dividing by 2. You are not subtracting 2. You're not square rooting 2. You're not doing any of that. All we're doing is ignoring the 2 and establishing the fact that then this exponent and this exponent must be equal, because this is a one-to-one function. There's no way, it could possibly equal anything else. There's no reasonable doubt if you were looking at a court case, So we have 3x minus 8 equals 4. And we love this. Why do we love this? It's linear. Who doesn't love a sweet linear equation? Linear equations are so sweet to solve. Add 8 to the other side. 3x is 12. Divide both sides by 3. X equals 4, and bing bang boom, we are done. There's no real need to check something like this for an extraneous solution, because the domain of an exponential is, as we remember when we were graphing, negative infinity to infinity, so there's no number that won't work when we plug it back in. When we change an equation and it turns it into a linear, sometimes when you modify in that way, you are introducing the chance that you get an answer that, while it works for a linear equation, it doesn't work for the original, and that would create what we call an extraneous solution. So you do want to check. Specifically, we need to check when the equation started off as a logarithmic equation, because we cannot take the log of a negative number or 0. Anyhow, next example. Now we have 27 to a power. We got 9 to a power. Can I write 27 as 9 to a power? No, I cannot. But what can I do? I can write them both as 3 to a power. So 27 to the x plus 3 equals 9 to the x minus 1. I'm going to do my swap-opportunity. I'm going to swap 27 for a smaller number to a power. I'm going to swap the 9 for a lower number raised to a power, and I want those numbers to be the same numbers. 27, and if you don't know your numbers raised to a power, this is where you're going to run into trouble and struggle. If your mental math, if your math facts are doo-doo, your performance on this will also be doo-doo, okay? 3 to the third is 27. Please don't screw it up and say 3 to the third is 9. 3 squared is 9. That's a common mistake I see all of the time, okay? But yes, you got to know your numbers to a power. I mentioned in another video that you really do want to know, like 3 up to maybe the 5th power, 4 up to the 5th, 5 up to the 4th, maybe 6, 7, 8, and 9. Know them up to maybe the 3rd power, because you need to know them for sums and difference of cubes anyway. 10 to any power, right? Now, what is the rule? Property of exponents. A to the m raised to the n. When you have that situation from algebra 1, algebra 2, we should know that we multiply our exponents. So we're going to do exactly that. 3 to the 3x plus 9 distribute. I don't know why so many of us are in the toilet with our distribution. We're like, yeah, it's totally going to distribute, and then you only multiply it by the first thing. That's not distribution. Did you not get the memo? Do you not know what distribution is? I guess not. Equals 3 to the 2x minus 2. And now, is it 1 to 1? Do you have 3 to a power equals 3 to a power? Yes, amazing, we do. We took care of our swap opportunity successfully, and now we will just set our powers equal to each other. 3x plus 9 equals 2x minus 2. Again, we have a beautiful, adorable linear equation, which we love. They're so easy to solve. Subtract 2x over to there, subtract 9 over to there, and where does that get me? We'll get x equals negative 11. Again, I don't need to even check for extraneous. I'm good to go. Happy times. Same idea. Next example. We have 5 to a power equals 125. This one's not too messy like B was, because I can leave this as 5 to the 3x minus 6 and 125. I told you, no, 5 up to maybe the 4th power. 5 to the 3rd is 125. 225 is not 5 to a power. That's 15 times 15. That is not 5 to a power, okay? 625 will be the next one. 5 to the 4th. Make sure you know it. So can we do our swap opportunity? You bet your butt. 5 is ignored, and we solve. We have 3x minus 6 equals 3. Again, we love it. It's linear. Lovely, linear. How cute and easy. Add 6 to the other side. We get 3x equals 9. Divide both sides by 3x equals 3. It was originally exponential with a domain of all real numbers. No need to check for extraneous or extra solutions. Lastly, we have what color do I want to write in? All right, 8 to a power and 4 to a power. You cannot write them both as 4 to a power. I usually gravitate toward the smaller number, but I can write them both as 2 raised to a power. 2 to the 3rd is 8, x plus 2. 2 to the 2nd is 4, x minus 3. We're going to multiply our powers. Can you maybe, write fewer steps? Sure, we could write. Distribute, though. 3x plus 6 equals 2x minus 6. Let's bring the 2x there and the 6 there. So x equals negative 12. It's not 0. Some of you will be lazy and get 0. Please write more steps if you are not a pro and you make careless errors. Write out your steps. X is equal to negative 12, and that is the end of these beautiful, adorable examples. Oh yeah, and that was our part time, that was our lovely linear. Now, sometimes they aren't linear. Sometimes you end up with a quadratic or some other polynomial, and that's okay. Those are cute too. We still love them. They're a little bit more work. They're not as easy as a linear, but they're easy peasy lemon squeezy. We should be good at those. We've been working with them for years, right? So that's the end of this video. This is the end of the first video in the set for section 4, which is a very, very crucial set. I would say a lot of these types of problems can be found mixed into calculus all over the place, especially at the end for AP Calc. AB at least. They're also all over your college placement test. I see this a lot to kind of help decide what level of math students should go into when they're getting into college. So make sure you are a pro at this section. If you are going to be taking that test soon, go through these videos, crash course, and get a good grip on them. Also the properties of logarithm section, which was, I think, the most recent one, section 3. Okay. Hopefully that was helpful. If you loved it so much, give it a thumbs up. If it made you frown, give it a thumbs down. Questions, comments, concerns, requests, and feedback, whatever you want, put it in the comment section below. Check the playlist on the screen right now for more videos on this topic, or you can check the description box where everything is super organized and there's links for everything. And that's it for now. Bye for now. Adios.